So we've done all the operations and stuff with numbers. Today what we want to take a look at is we want to look at starting out the concept of a variable. And I know a lot of people cringe when we start talking about variables, but that's why we bring it up early in the course, so we got time to go over it and develop the idea. And it's really not as big of an issue as what most people make it out to be. It's not something to really panic over. A variable is just an unknown number. In fact, that's one way to define a variable. If you just say an unknown number, we can represent it then with a letter. A lot of times we use X or N, or probably two of the more common ones, sometimes Y. We can use any letter, though. We could use A, B, C, any letter we wanted to represent it. In some cases, they'll even use like Greek letters and stuff like that to represent variables. Any symbol really that we want to, other than a number, can be used to represent it. And like I said, all it stands for is an unknown number. But we often combine those with other things. So let's look at a phrase like 8 more than a number. Well, this is implying we still have an unknown number. That unknown number I'm going to call X for now. You could call it N or Y or whatever. 8 more means what? Plus. We've added 8 to it. 8 more than the number is the number plus 8. So X plus 8. Now there are a lot of other phrases out there that would imply addition, that would imply X plus 8. We could have a number increased by 8. That would be X plus 8. The sum of a number and 8. Or we could just have a number plus 8, or 8 added to a number. All sorts of phrases that imply addition. So that's the first thing you need to do, is start picking out those phrases that imply addition. Increased or more than. Sum means the result of an addition problem. We might have 5 less than a number. Now, a lot of people mistakenly do this. 5 less than a number. No, that's not what it means. It is good thinking, but it's not right. If it said 5 is less than a number, then that's what it would be. But 5 less than a number is simply X minus 5. 5 less would be subtracting 5 from it, taking 5 away from it. There's all sorts of other phrases out there. We could have a number decreased by 5. Or a number subtract 5, take 5 away from a number. One of the key words, difference. The difference of a number and 5. The word difference means the result of a subtraction problem. Now just a little side note, 5 less than a number is X minus 5. 5 less a number, that is 5 minus X. Saying 5 less a number. So you're taking the number away from the 5 instead of 5 away from the number. So there are some very subtle little things like that you have to be careful of. We'd have a phrase like the product of 3 and a number, or the product of a number and 3. It really doesn't matter. What's product? What operation does product indicate? Multiplication. So bless you. The product of a number and 3, bless you again. So the product of a number and 3 would indicate 3 times X, or usually just write it as 3X. If you wrote X times 3, that's fine as well, because product can be, remember we talked about commutative last Thursday, can change the order. But there are other phrases. I mean, you could have 3 times a number, a number multiplied by 3, all sorts of phrases that would indicate multiplication. But the big key word there again is product. Just like sum, difference, we have product describes multiplication. We have a number split 4 ways. This is kind of one of the more unusual ways to express this operation, but of course this is division. So x divided by 4, or we could just do x over 4, also indicates division. And there are other phrases.
Well, how do you know you're not just dealing with
a fraction?
Yeah.
A fraction and division kind of have some interchangeable aspects to them. A division problem can be turned into a fraction, and a fraction can be turned into a division problem.
Okay.
So now there are other phrases that indicate division. You can say a number divided by 4, or the quotient of a number in 4. Quotient is the result of a division problem. So doing these single operations, you have to look for those keywords and first figure out the operation, and then of course, addition and multiplication, the order that you put them in doesn't matter, but subtraction and division, you got to be a little more careful. Now, sometimes we'll bring in more than one operation, like this. We might have 3 times a number increased by 8. What's that going to look like? Well, of course, we have a number, which we'll call x.
So
3 times x would be just 3x plus 8. Very good. Now, this next one's going to look like it might be the same, but there's a very subtle difference. 3 times the sum of a number and 8. Now here you're looking at it thinking, well, we add 8 and we multiply by 3. It's the same thing, but it's not. Up here it was 3 times a number. That's why it's 3 times x. Here it's 3 times the sum. What is a sum? The sum is the result of an addition problem. So this is saying we do the addition first and we multiply that result by 3. So the sum of a number and 8 is x plus 8. That result gets multiplied by 3. So you have to have the parentheses in there. Remember we talked about the order of operations. We have to have the parentheses in there to state that in this case, we add first and then we multiply by 3. So just translating, and I told you guys yet last week that we covered the operations with negative numbers and how I said that was probably the second most difficult concept in math. This right here, translating from words into formulas and symbols, I believe is the single most difficult thing in math. Now, these are relatively simple problems, but we get into more word problems where you have to pick out the word problems and put number, create an equation to solve. I mean, it can be tough. I mean, so bear with it. We're going to practice this over and over again. We're going to circle around and come back to word problems over and over again throughout the semester. So hopefully they won't hurt near as bad by the time we're done. Once we have things in the symbols, we need to be able to do things with them. So we might need to look at issues like this. If we have 5x and 7x, what do we get? Well, just like any other number, we're going to combine the counts. So 5 plus 7 is 12, and we keep the same name. So it's just x. What if we have 8x plus 5y? What do we get? We get 8x plus 5y. When we add or subtract, we have to have the same name. We can't add x's to y's. Now we might run into something like this. Can we do anything with that? No. X and x squared are not the same. An inch and a square inch are not the same. So an x and an x squared are not the same either. We cannot add those. That is just 5x plus 7x squared. In fact, in a little bit, I'm going to show you how that's actually just a single number. It's not even really two numbers. Yeah, Cody?
I'm pretty sure the elder was supposed to do everything
It doesn't work real well. No, you're right. I run a construction company in the summers, and I can tell you that doesn't match up. So anyway, however, we may run into things like 9x plus 7y plus 3x minus 4y. Now, even though there are different names here, there are still some things we can combine. We have 9x and 3x, which can combine to make 12x. 9 plus 3 is 12. X stays x. Now, we have to be careful with this next part. We have 7y, and this is not 4y, but negative 4y. The symbol in front of it, this is a plus, so that's a positive 3x. This is a minus, that's a negative 4y. 7 and negative 4 make 7 and negative 4 end up at 3. So it's a positive 3, so we put a plus here, plus 3y. Now, I said something about this, that's actually just a single number. There's a good reason for that. It's actually true. If we look at our place values for numbers, this is the ones, the tens, the hundreds, the 1,000s, 10,000s, and so on. What that really is this is 10 to the power of 0, which is just 1. 10 to the 1, 10 squared, 10 to the third. If I were writing out numbers in expanded form, let's say I had 7,284, I could write that as 7 times 10 to the third, or 7,000s, plus 2 times 10 squared, or 200s. This is just an abbreviation for thousands and hundreds. Plus 8 times 10 to the 1, plus 4 times 10 to the 0. Well, the same with an algebraic number. I might have 8x squared plus 2x plus 9. Well, you can see what that is the digits now, instead of being the place values being tens, the place values are x's. This is the x to the 0 digit. That's x to the 0. Anything to the power of 0 is 1. We'll go over that in a couple classes. This is the x to the 1 digit. This is the x squared digit, and so on. So this here, it looks like it's 3 separate numbers. It is not. It is a single number with 3 digits. And when you go to work on it, it behaves just like any whole number and its place values. In fact, one of the differences is, of course, you can't abbreviate this as just 829. You have to write the place values in there. You have to have the x squared, the x, and of course, you don't put a place value on the 9. So that's one of the differences between these algebraic numbers and whole numbers. The other difference is in a whole number, every digit must be positive or every digit must be negative. If I have negative 239, that is a negative 2 hundreds and a negative 3 tens and a negative 9 ones. I could have wrote the words hundreds and tens and ones in here if I wanted to. But on an algebraic number like this, often called a polynomial, by the way, in a polynomial, each digit can be positive or negative on its own. I can have 7x squared and negative 3x and a positive 9. And the final big difference between them is, in a whole number, the digits are limited to go between 0 and 9. In a polynomial, in an algebraic number, they don't have to be. This could be 2x squared plus 15x minus 11. Each digit can be as big as you want it to be because there is no carryover into the next place value. Now, with this in mind, when you do some operations with these algebraic numbers, they end up working just like whole numbers. If I have like 5x squared plus 3x minus 7, and usually the book will put those in parentheses just to keep them separated, plus 2x squared minus 13x plus 4. The book talks about just you take the parentheses away and they call it combining like terms. Well, that's just combining the digits that have the same place value. We could actually do this just like we do whole numbers. We write out the one digit on top, and then we put the next, or one number on top, then we put the other number below it, lining up the digits, lining up the place values. So the 2x squared goes under the 5x squared. Negative 13x goes under the 3x. The 4 ones goes under the negative 7 ones. And now we can add. Now we have to be a little careful because we have negatives in here. What's a negative 7 plus 4? Negative 3. 3 plus a negative 13? Negative 10. That's a negative 10x. And 5 plus 2 is 7x squared. And there it is. It's just like adding whole numbers. It can be a little tricky because we can run into things like this. We just have to make sure we line up the place values, line up the digits. So I have the 9x squared minus 5x plus 3. Where's the 8x squared have to go? Under the 9x. Where's the negative 7 have to go? Under the 3. There's a missing digit here. There's the x digit is missing. So anyway, we got 3 and negative 7 make negative 4. Well, negative 5x doesn't combine with anything. 9x squared and 8x squared is 17x squared. When we subtract, it works the same way. In the book, they tell you drop the parentheses and then change every sign on every digit in that second number. So this would be a negative 3x squared, negative 12x, positive 9. But what we're really doing there is we're just adding or subtracting numbers, just like we would whole numbers. So we set it up, lining up the place values of the digits. The difference is now we're subtracting down each column. So what is 13 minus a negative 9? Well, 13 minus a negative 9 is 13 plus 9, or 22. Gotta be careful. Remember, when you do subtraction, you change it to plus the opposite. Negative 7 minus 12. Change it to negative 7 plus a negative 12, which is negative 19. So negative 19x. We're struggling with the negatives still, aren't we? Yeah. It'll take a while to get used to them. Then 5 minus 3, of course, is 2x squared. These rules for subtracting with the negatives, they look familiar once you see it. It's just struggling to do it on your own, or are they totally foreign to us yet? When we see these negatives here, like the 13 minus the negative 9, is that one of those things, you just forgot it, but once you saw me, it looks familiar? Or no, you're looking at it having no clue if you could ever do that on your own at all?
The subtraction is just throwing me.
The subtraction is tough. And when you look at this, of course, it's not so obvious. That's why I write it out over here. Because 13 and negative 9, well, no, we're subtracting. So it's 13 minus a negative 9. So now then I have to remember, I change this to plus the opposite. Plus, opposite of negative 9 is positive 9. Right. And negative 7 minus 12, negative 7 minus 12 becomes negative 7 minus negative, or plus a negative 12. So then negative 7, negative 12 go the same direction. Right. It's going to take some time to get used to the negatives, especially in subtraction. When we multiply, we said we multiply counts. 5 times 7 in this case is 35. But we also multiply the names. So x times x would be, yep, x times x or x squared. It's like inches times inches is inches squared.
Oh, right.
Because of that, we don't need the same name. Just like we did feet times pounds to get foot pounds. Here, 5x times 2y. Well, 5 times 2 makes 10. And then x times y is xy. Like that. We can have more than one variable. Well, let's do this one next, actually. We'd have like 7x times 4x to the third. Now, x and x to the third are different, but we can still multiply. When we multiply, we don't need the same name. 7 times 4 is 28. X times x to the third is actually x to the fourth. This is x. X to the third is 3 x's. We multiply them together. We're going to have 4 x's multiplied together, or x to the fourth. We'll look at those rules for powers a little bit more in the coming classes. We might have something like this. So we can do 4 times 9 is 36. Now when we have more than one variable, we do each of them at a time. Let's do x times x is x squared. Y times y is y squared. We can run into this. So we go to multiply. Multiply the counts. 3 times 5 is 15. X times x, x squared. Now we've got the y, but there's nothing to multiply the y by. It just stays y. We got the z, nothing to multiply that by, so it just stays z. So 15x squared yz. What do you think? It's going to take a while.
I think I'm still going home and watching this again.
Okay. Anyway, we can divide too. We're just going to stick with the single digit numbers for a minute here. And we can divide as well. We might have 12x divided by 4x. We divide the numbers. And again, I wrote it as a fraction, but that is still the same as just 12x divided by 4x. When we're dealing with variables, it's just easier for me to see it written like this. So, just like multiplication, we're going to combine the counts. 12 divided by 4 is 3. And then we're also going to combine the names. X divided by x cancels out. It's 1 or nothing. So that divides out to be just 3. I could also have something like 27x squared divided by 3x. Well, what is 27 divided by 3? 9. X squared divided by x? Well, x times x equals x squared, so going backwards, x squared divided by x has to just be x. Okay, so we've done the multiplication and division with the single digit numbers. What happens when we have more than one digit? Like, well, we might have like 8 times 5x plus 4. Now, many of you, if you had algebra in high school, you learned something called distributing. Or distribution. All that is basically this. You're going to take this number out in front of the parentheses, you're going to multiply it through. 8 times 5x is, well, 8 times 5 is 40, and there's nothing to multiply the x. Then you have 8 times 4 is 32. It's a positive 32, so plus 32. That's distributing. But in reality, that's just a shortcut. This multiplies out the same way that whole numbers do. If I had like 3 times 21, I would have 21 and 3. I'd do the 3 times 1 is 3, 3 times 2 is 6. So I have 3 1s and 6 10s, or 63. I would do the same thing here. I'd put the 5x plus 4 on top, multiply by 8. 8 times 4 is 32. It's a positive 32, so it's plus 32. 8 times 5x is 40x. You can see I get the same answer. Now, the distributing was a little bit shorter, took up less space. But this is really what's happening. It's a long multiplication.
I have a question.
Yeah.
What's in parentheses first? How come we don't wait?
Okay, very good question. If we're supposed to do what's in the parentheses first, why don't we? Well, because here, 5x plus 4 is not an addition problem. It's a single number written out in long form. Just like if I have 27, if I write that out as 2 10s plus 7 1s, it's not asking me to add them together because I can't. They have different names. It's a whole number. Same here. This is not 5x plus 4 because I can't add those because this is x's and this is just 1s. So a parentheses can serve two purposes. One is it can tell us we have to do something here first. But the second purpose is just separating part of a number from the rest. Like when we did our operations with negatives, the parentheses told us separated that negative, so it's a -3 and not a -3.
If the x wasn't up there, then you could do parentheses first.
Yeah, if that was just 5 plus 4 in there, then you would have to do what's in the parentheses first. We can run into things like this. 3x times, and then in parentheses 2x minus 4. Now you're right, we should check. Is there anything we can do inside the parentheses? No, there's not. So then the next question would be, is there anything that needs to be done to the parentheses? And the answer is yes. It's being multiplied by 3x. So let's do that. 2x minus 4 times 3x. 3x times -4 is, well, 3 times -4 is -12. Then there's nothing to multiply the x. How about 3x times 2x? Perfect. 3 times 2 is 6. We also multiply the names, though. X times x is x squared. And, of course, we could have just done distributing over here if that's the way you're used to doing it. I'm not going to stop you. Just 3x times 2x is 6x squared. 3x times -4 is a -12x. You get the same answer. To me, this makes more sense, but as we move along and we get better at this shortcut, it does save some time and space, and we will start doing it the short way like that eventually. Just like with whole numbers, we can have an order of operations problem. Now, looking at this, it probably doesn't look much like an order of operations problem, but it really is. It'd be not much different than having like 2 times 5 minus 3. Here, we would multiply the 2 times 5 and then subtract 3. Do the exact same thing over here. We're going to multiply the 8x times the 3x plus 7, then we'll subtract 8. So let's do, actually I should have done this. I'm gonna get rid of the x there. We're gonna just 8 times the 3x plus 7 and then subtract 8. So I'm gonna do the 8 times the 3x plus 7. So I'm gonna multiply by 8 here. 8 times 7 is 56, so positive 56. 8 times 3x is 24x. Then we have minus 8 here. Now we're taking the 24x plus 56 and we're subtracting 8 from it. Where do I subtract the 8 from? 56. Good. So the 24x doesn't change. 56 minus 8 is 48. Remember, you think of this like this. 24x plus 56 minus 8, so 24x plus 56 is the first number. We're subtracting. The 8 has to go under the other one, so the 8 gets subtracted from the 56. Okay, so now here, again, this is an order of operations problem. Look in the parentheses. Is there anything to do in the parentheses? Either one? No. So that means we're back to then just anything that needs to be done to the parentheses. And in this problem, all it has is multiplication and addition. We're going to do the multiplication first, and then we'll add. So I have this 3x times the 2x minus 4. So I'm going to do that part first. I'm just going to use the distributing instead of long multiplication just to save some time. So 3x times 2x is 6x squared. 3x times negative 4. 3 times negative 4 is a negative 12. And that's just the x. Now over here, 7x times 8x. Well, 7 times 8 is 56. X times x is x squared. That's positive, so I'm going to put plus in front of it. 7x times 1. 7x, again, it's positive, so I put a plus in front of it. Now, I can add. I can either, set it up by moving things around, or I can just look at it and say, okay, I've got 6x squared, 56x squared, which makes 56 and 6 makes 62, x squared. Negative 12x and positive 7. Well, negative 12 and positive 7 makes negative 5x. What do you think? It's going to take some practice? Mm-hmm. Okay. Well, with that, let's let you practice. You'll have a new homework. You'll have a quiz, your first quiz, which will be due tomorrow, Tuesday, 11:59 p.m. And your second homework, homework 2, which will be due for Wednesday. At class time, sometime during class.